Midterms in Algorithm and Complexity. Hi everyone! Hi Prof. Doc Alagos. Now, I'm going to present about Introduction to Big O Notation and Time Complexity, presented by me, Herby G. Estrella, PSCS, 3 New Mod, First Year, Second Term, 2023-2024. Now let's start about time complexity. Time complexity provides a generalized way to express algorithm speed regardless of input size or other factors. Directly measuring the runtime isn't effective due to various computer speed and input size. Next is Big O notation. Time complexity is often expressed using Big O notation. Big O classifies algorithms based on their behavior as the input size increases. Different types of time complexities. First is linear time complexity, O of n. As the input size increases, the time taken increases proportionally. It is represented as O of n, efficient for moderate size inputs and common in basic search algorithms. The following Python code defines a function called findSum that takes a list as an argument array and returns the sum of its elements using the built-in sum function. The code then creates a list array with elements 1, 2, 3, 4, 5, calls the findSum function with this list, and prints the result. The code defines a function findSum that calculates the sum of the elements in a given array. The function uses a for loop to iterate through each element of the array and adds the element to a running total. Finally, the total sum is returned. Second is constant time complexity, O of 1. Describes as an algorithm where the execution time remains constant regardless of the input size. Ideal for small tasks, its execution time does not depend on the size of the input and it is represented as O of 1. The given Python code defines a function named pairwise comparison optimized that takes a list array as input. The function compares the elements in the list pairwise and counts the numbers of occurrences where the right element is equal to twice the left element. The function uses a dictionary countDict to keep track of the count of each element encountered so far. The variable count is used to accumulate the total count of valid pairwise comparisons. The code defines a function named pairwise comparison optimized that efficiently counts the number of identical pairs in a given array instead of using a nested loop which would result in quadratic time complexity. The code employs a dictionary countDict to keep track of the count of each unique element in the array. The third one is quadratic time complexity, O of n squared. Time increases exponentially with input size. It is represented as O of n squared, inefficient for larger inputs and common in algorithms with nested loops. The provided code defines a function called pairwise comparison that takes a list array as input. The function counts the number of pairwise comparisons where two elements are equal in the list. The code uses a set to obtain unique elements in the list and then iterates through these unique elements to count the occurrences and calculate the pairwise comparisons. The code defines a function named pairwise comparison that counts the number of pairwise occurrences of identical elements in a given array. The function utilizes a nested loop structure to iterate through each element in the array and compares it with every other element. For each pair of matching elements, the count is incremented. The final count of pairwise occurrences is then returned by the function. The fourth one is logarithmic time complexity, O of log n. Each iteration reduces the problem size by a fraction. It is represented as O of log n. As the input increases, the number of operations grows logarithmically. The Python code appears to be an implementation of binary search for finding a target element in a sorted array. Before proceeding with the binary search, the code checks whether the array is sorted. If the array is not sorted or if it is empty, the function returns in -1. Otherwise, it performs a binary search to find the target element. The algorithm works by initializing 2 pointers, low and high, at the extremes of the array. It then enters a while loop that continues until the low pointer exceeds the high pointer. Inside the loop, the middle index, mid, is calculated and the element at this index is compared with the target. If they match, the index is returned as the result. 5 is linear arithmetic time complexity. O of n log n occurs in algorithms that combine linear and logarithmic operations. It is represented as O of n log n, commonly found in efficient sorting algorithms like merge sort and heap sort. The overall efficiency is better than quadratic but worse than linear. The code is an implementation of the merge sort algorithm in Python. Merge sort is a divide and conquer algorithm that recursively divides the array into halves, sorts of each half, and then merges them back together. The given code implements the merge sort algorithm, a divide and conquer sorting technique with a time complexity of O of n log n. The code ensures a logarithmic time complexity by repeatedly halving the input size during the recursive calls, making it an efficient sorting method. 6 is cubic time complexity. O of n cube represents algorithms with 3 nested loops or operations that grow cubically with input size. It is represented as O of n cube, considered less efficient than quadratic algorithms and can be resource intensive for larger inputs. The Python code defines a function called cubic operation that performs a cubic operation on the elements of an array. It uses 3 nested loops to iterate through all possible combinations of array elements and calculates a product of elements at indices I, j, and k. The results are accumulated in the variable result. The function iterates through every combination of 3 indices I, j, and k in the array, ensuring that it covers all cubic interactions. Finally, the cubic sum is returned as the result. It's important to note that cubic time complexity algorithms, as illustrated by this code, involve a high degree of computational overhead and may not be efficient for large input sizes. Number 7. Exponential time complexity. O of 2 to the n. Each increased input size doubles the number of operations. It is represented as O of 2 to the n, often seen in brute force algorithms where all possible combinations are explored. Becomes impractical for larger inputs due to the rapid growth in the number of operations. The Python code defines a function called generate subsets that generates all possible subsets of a given set S. It uses binary representation technique to determine which elements are included in each subset. The resulting subsets are stored in a list and returned. This implementation has an exponential time complexity of O of 2 to the n due to the exhaustive generation of all possible subsets. The bit manipulation technique allows for a more efficient way to explore the power set without relying on recursive calls, making it suitable for larger input sets. Asymptotic analysis. Coefficient and constants become less significant as the input size grows to generalize algorithm efficiency. Emphasize that asymptotically more efficient algorithms will eventually be faster. Additional, when determining big O, coefficient and non-dominant terms are dropped. Example given at the lecture, where a function with O of n squared and O of n components is simplified to O of n squared. The types of time complexities in order from good to bad in terms of efficiency. Let's see the illustration. If you see the 7 types of time complexity in this plot, it is pretty clear that in this order, the time complexity gets good to bad. When you compare an algorithm that is asymptotically more efficient than others, then is guaranteed to be faster eventually as you keep increasing the input size no matter what constants or the coefficients. And you're trying to decide which is the dominant term in your algorithm, you need to pick the worst one, which is you can decide from this order. Thank you for watching. Please comment down below what are your more questions submitted to Prof. Doc Alagos. Thank you for watching.